Hi everyone, welcome to the Arithmetic Zone. Today we have a video for you guys on deriving logarithmic properties. And this is basically just going to go over the different characteristics of the logarithm that makes it so useful in math. And we're going to just go over why they exist and the mechanics behind them. So first, for a quick overview of logarithms, they serve as the inverse to exponential equations, which can be used to find an unknown exponent given the base and the answer. So here we have the general form of the logarithm. We have the log of some base a of b, that's going to be our argument, is equal to c. Now, they have exponential equivalent. So this statement is equal to a to the c power is equal to b. So a is the base, b is the answer itself of the exponential. It's on this side of the equal sign. It's what this yields. And c is the exponent. So as you can see, this logarithmic part of the equation actually yields c. This is the output, which is why they can be used to find an unknown exponent. That's what they give out. That's their output. So I have it rewritten on this part of the slide. And we're just going to go over the first two basic properties of logarithms, the zero and the identity property. So in order to do this, we're going to reconstruct the logarithm that we see here and put it into its exponential form. So starting with the zero property, we have log base a of 1 is equal to 0. So writing this in its exponential form, we have a, that's our base here, of 0, because that's our exponent, is equal to 1. Now this should make sense because any real number raised to the 0 power is going to be equal to 1. So if this statement is always true, and these two statements, correlate to each other, then this statement must also always be true. So no matter what the base is, if the argument is 1, the output will always be 0. Now for the identity property. Log base a of an argument a, they're the same number, is equal to 1. Now writing this out in its exponential, we get a to the first power is equal to a. This again should also make sense because any real number raised to the first power is going to equal to itself. And if this statement is always true and it corresponds to this statement, this log statement, then this log statement will also always be true. If the base and the argument are the same, it's always going to result in a 1. And this is actually why ln of e is equal to 1, because ln is just another way of saying log base e of e is equal to 1. The reason for the different notation is because this log is used so often in fields like calculus that it merits its own different notation of a logarithm, but it still functions in the same way. So these are the 4 different properties that we're going to look at: the product, power, quotient, and change of base rules. They're listed out here, but they will also be listed out in the slides that come ahead, and we're going to look at them more in depth there. So starting with the product rule, we have to prove that log base a of some product of two numbers bc is equal to the log base a of b plus log base a of c. Basically, you can split apart that product into two different logarithmic sums, essentially. So for most of these questions, we're going to set the base a equal to 10. So I can rewrite this statement as log of bc is equal to log b plus log c. Now I don't have the subscript written because log base 10 is a common log, so we just write it with no subscript. If there's no subscript, it's assumed to be a 10. Now for this derivation, we're going to have to think a bit outside of the box. I'm going to assign every single portion of this equation to a variable. So I'm going to let log of b equal to x. We're going to let log of c be equal to y. And finally, we're going to let log of bc be equal to z. And I want to rewrite this in their exponential equivalence. So this is the same as saying 10 to the x power is equal to b. This is the same as 10 to the y power is equal to c. And finally, this is the same as saying 10 to the z power is equal to the product of b and c. Well, we know what b is. We've defined it as 10 to the x, so we can plot that in there. And similarly for c, we know what c is. We've defined it as 10 to the y, so we can plop it in there for its position for c. And so rewriting this statement, we have 10 to the z power is equal to the product of 10 to the x and 10 to the y. Now focusing on this side, if we have a product of two numbers with the same base, we can add the exponents. So we have 10 to the z power is equal to 10 to the x plus y. Now, if we have an equation with both sides of the equation having the same base, we can now just focus on the exponents. This is the one-to-one property. Now we have z is equal to x plus y. Now let's sub back in what z, x, and y originally were. Z was log of bc, x was log of b, plus y, which was originally log of c. And this statement right here was what we had originally, making it an identity. This is the proof for its identity and its validity as a logarithmic property. Now for the power rule, we're going to prove that log base a of some argument b to the c power is equal to c times log base a of b. Basically, what this is saying is you can pull out this c outside of the logarithm. This is actually one of the more useful properties of the logarithm, so it is very useful to know the derivation of it. And this is going to use properties of the product rule proof. So I'm going to give an example. We've already established that log of a product of numbers a, b, these aren't the exact letters that I use, but it still holds true, is equal to log a plus log b. Well, this also works true with exponents, because an exponent, let's just say b squared for now, is just repeated multiplication. So in this case, it'll be b times b. So it can be rewritten as this repeated addition of log statements, log b plus log b. But instead of using an exponent of 2, let's make it any number c. It's going to be some unknown c. Log of b to the c power. This is going to be equal to log of b times whatever number is specified by the c. The c tells us how many times b is being multiplied to itself. So rewriting this using the product rule, this takes on the form of log of b plus log of b plus how many ever times the c specifies us to. Oh, I apologize. That should have a b there. The c is basically indicating us how many of these log of b terms we're going to have. This is also c number of times. So in order to really see how the proof plays out, I'm going to set log of b equal to some variable y. So instead of log b's being repeated c number of times, we're going to have y plus y plus y, some number of c times. Now, if you just have one set of these y plus y's, we would say it's equal to 2y, with 2 being the number of instances that the y is being added to each other, right? So if we have c instances of y being added to each other, we would say that this is equal to cy, c indicating how many times it's added to each other. So let's just replace the y with what it was originally. Now we have c times log of b. There are c instances of log of b in this statement, and this is actually what we had originally, again, proving its validity as a proof. Now we have the quotient rule. We are tasked with proving that log base a of some quotient of two real numbers, b and c, is equal to log base a of b minus log base a of c. Very similar to the product rule, where if we had a product of two real numbers, we can express them as the sum of two logs. And now if we have a quotient of two real numbers, we can express them as the subtraction of two logs. This is going to employ properties of the product and power rule proof. So I'm going to reconstruct this. We're going to focus on this right-hand side as opposed to the left-hand side. So log base A of B minus log base A of C can actually be rewritten as log base A. Actually, I'm going to let A be equal to 10. We're going to work with common logs again. Log of B plus a negative log of C, because subtraction is really the same as adding a negative quantity. And so now I want to focus on this part right here. I'm going to work to the side, negative log of C. This is really the same as -1 times log of C. And we've already established with the power rule that if you have some exponent in your argument, you can pull it out. Well, the reverse is true. If you have some product to a log, you can put it into the logarithm as well. This is equal to log of C to the -1 power. So let's rewrite this. This is going to be equal to log of B plus, the negative is gone now because we're going to put it inside of this log. So this is going to be plus log of C to the -1 power. Now we can rewrite that inside of that logarithm, C to the -1 power is really just equal to 1 over C. And now that we have the sum of two logs, we can employ the product rule proof where we had it as log of B plus log of C is equal to log of BC, We focused our efforts in deconstructing this, but if we have two separate log statements that are being added together, we can multiply them under one log as shown here. So that's what we're going to do with this example. We're going to multiply the two arguments and put it under one log. This is going to be equal to the log of B times 1 over C. And simplifying that down, we get log of BC, which is the division of the two logs that we had originally, which cements the quotient rule as an identity. Now, finally, for the change of base rule. This one, we won't set anything to 10 for the common log, because this one is important to see how the variables work out. So we have log base A of B is equal to log base C, this is a new base, the change of base, of A being our original base, over log base C of B, our original argument. So for this setup, we're going to again have to work around the box here. We're going to start with this left-hand side. We're going to let log base A of B, the left-hand side, be equal to X. Okay, and now rewriting this in its exponential form, we have A to the X is equal to B. Now let's apply the log of this new quantity to both sides of this equation. So using our new base C, we have log base C of A to the X is equal to log base C of B. We want to work with this new C because this is what leads us to the change of base rule identity that we have highlighted there. Now we're going to use the power rule. We're going to pull this X outside of the logarithm. We're going to have X log C of A. So the argument is just going to be A now is equal to log base C of B. And now we're going to isolate A, or rather X. We're going to multiply by log base C on both sides of A, log base C of A on both sides. And now we have that X is equal to log base C of B over log base C of A. And X, we're going to sub in what X was originally. X was originally log base A of B. And now we're just going to copy down what we had here, because that side of the equation doesn't change. And this is the exact same statement that we have up here. Oh, excuse me, this should actually be swapped. I apologize for that, but it does come out to be this answer. So that is just a quick overview on logs, kind of showing you where their functionality comes from. I hope this was useful to you, and I'll see you guys later.